Today's topic, Sn1 reactions. This lesson requires familiarity with nucleophiles, electrophiles, carbocation, and reaction rate concepts. Sn1 reaction is a type of nucleophilic substitution reaction. Substitution means replacing one thing by another. Thus, a nucleophilic substitution reaction means substitution of one nucleophile by another, as shown here. Just a quick note, we're talking about substitution reactions at the saturated carbon. These reactions are different than substitution reactions at carbonyl groups. Sn1 stands for substitution, nucleophilic, unimolecular. The unimolecular means that only one molecule, the electrophile, as we'll see, is involved in the rate determining step. Let's look at the reaction of third butyl bromide with sodium hydroxide as a general mechanism for Sn1. In the first step, the bromide ion or the leaving group leaves, giving a carbocation intermediate. This is the rate limiting step, and so the overall rate of the reaction is determined by this step. The nucleophile, hydroxide ion in this case, then attacks the carbocation intermediate in the second step, giving us the substitution product. So the hydroxide ion replaces the bromide ion, and hence the name nucleophilic substitution. Now let's look at this carbocation intermediate. Reaction of this carbocation intermediate with the nucleophile results in the formation of a chirality center. The carbocation is planar and thus can react with the nucleophile equally well from either side, and thus a racemic mixture of enantiomers is obtained. However, the ratio is not always exactly 50-50. So the two most important points in Sn1 reactions are as follows. First, Sn1 reaction rate depends only on the alkyl halide concentration or the electrophile and is independent of the nucleophile concentration. In other words, the reaction is a first-order process. Second, the intermediate can react with a nucleophile equally well from either side, leading to a racemic mixture of enantiomers if a chirality center is formed. Now let's see what factors affect Sn1 reactions. The first contributing factor is the stability of carbocation. Since the formation of carbocation is the rate-limiting step, the reaction is favored whenever a stabilized carbocation intermediate is formed, which also results in a stabilized transition state. The trend of carbocation stability is shown here, with tertiary, benzylic, and allylic carbocations being the most stable. Thus, the corresponding halides are more likely to undergo Sn1 reactions. If you want to know more about carbocation stability, there is another video which explains the concept. The leaving group is the next factor influencing Sn1 reactions. The best leaving groups are those that best stabilize the negative charge in the transition state. The groups that best stabilize the negative charge are the weak bases. Thus, bromide ion, iodide ion, and tosylate make good leaving groups, while strong bases such as hydroxide make poor leaving groups. Remember, hydroxide is a strong base and is looking for a hydrogen ion, and therefore it is not a good leaving group as it is not happy on its own. Lastly, the rate of reaction also depends on the choice of solvent. Sn1 reactions are favored in polar protic solvents. Protic solvent is a solvent which can form hydrogen bonds. Remember, we're forming a carbocation intermediate, and thus any factors contributing to its stabilization should increase the rate of the reaction. More precisely, the transition state is more polar than the starting material, and so is stabilized by the polar solvent. A strongly polar protic solvent such as water and methanol can stabilize the carbocation as the electron-rich ends of the solvent molecules orient around the positively charged carbocation. So in this example, oxygen atom in water with its lone pair of electrons and the partial negative charge orients itself towards the positive charge of carbocation. So how about the nucleophile? For Sn2 reactions, the nucleophile is also a factor influencing the reaction. However, for Sn1 reactions, the nucleophile doesn't matter. That is because the rate of the reaction depends on the rate determining step, which is the formation of carbocation, and depends on the substrate and not the nucleophile. Neutral nucleophiles work just as well as negatively charged nucleophiles. In conclusion, Sn1 reactions have two steps: formation of carbocation intermediate followed by the nucleophile attack. The reactions are favored with substrates leading to the most stable carbocation, with weak bases as the leaving groups using polar protic solvents. Thank you for watching.